In the name of God, today's topic is going to be about viscosity. Okay. Viscosity, based on or is one of physical quantity that can be calculated associated with some properties of gas molecules. In general, viscosity is related to fluid systems, for example. So here sort of the behavior of a gas is taken to be like that of a fluid. But before I dive into the topic of viscosity, I think it's worth mentioning that the last set of topics to be addressed are as follows. Somehow these are going to be transport properties, of gas, let's say of gas in non-equilibrium but steady state. Okay. What we have addressed earlier, for example, pressure was some sort of property of the gas with the gas in an equilibrium state. Okay. But here the last set of topics, okay, one of them is viscosity, it's related to properties related to the gas in non-equilibrium but steady state of the gas. These are transport properties. One can see somehow that the transport of transverse momentum, so as the gas molecules move around inside their container and interacting possibly with some external factors, there could be transport of some things from one part of the gas system to another part of the gas system, right? An example is transport of transverse momentum, which is going to lead to this property or concept of viscosity, right? The transport of heat energy by gas molecules is going to lead to something called thermal conductivity, how heat is transferred from one part to the another. Depending on the gas molecules, this is going to be different for various molecules, right? So thermal conductivity, right? And another, the last transport property we're going to consider is the transport of molecules or particles themselves. Transport of molecules, this leads to the concept of diffusion, right? So for example, some perfume molecules released at one corner of a room would diffuse with time, and it's going to reach some other part of the room. So these are physical properties, physical phenomena, which one can explain, which one can make predictions about using kinetic theory of gases. Okay, so we shall start with viscosity, as mentioned. Again, before that, we're going to make use of the following. Maybe you have seen them for sure somewhere else. The definition of tensile stress and shear stress, right? Tensile stress has to do with some sort of the effect of a force on a given material. Okay, so the material can be some solid material, it could be like a fluid, it could be a gas, as would be our case here. So tensile stress is due to force perpendicular to area, is due to force which is perpendicular to some area A. On the other side, one can consider shear stress, and this is due to force on a system or a material which is parallel to some area under consideration, so area A. By definition, shear stress, if we represent that with tau, let's say tau star, to differentiate it with tau that we have used earlier, mean time between collisions. So tau star here is shear stress. It is force applied over the area, right? So F is a component of applied force, which is parallel to A. And A could be some cross-sectional area of the material or system under consideration. Okay, so the shear stress tau star can lead to the formation of material under consideration. So these are general discussions, but we're going to apply them for the case of a system where the system or the material is going to be a gas. Okay, so an example of this deformation is, for example, one can consider, let's say, a system or a material that has, let's say, this shape, maybe a rectangular shape. Okay, but because of some applied force on this lower side of the material, let's say this is F. Okay, let's say the force is applied on the upper side of the material. So initially the shape of the material is with the dashed lines, and there is a force applied on the upper side, so we have F not equal to 0 on top, but on the lower side there isn't any force applied, so F is equal to 0 on the lower side. This F is going to lead to some stress on the material, and that stress can make the shape of the system to get deformed. So initially it was a rectangle, but because of the shear stress it gets deformed, right, as shown like in this sketch, which you can see. So there is a change here in length. Let's say this is delta L due to the force F here not equal to 0. And so viscosity is related to shear stress, and it is a measure somehow, viscosity, a measure of the resistance of the material or gas, we are considering gases, a measure of the resistance of the material to the deformation due to shear stress. Due to, let's say, tau star, right? So these are two nodes, 1, 2, just to kind of see the link between the two things. One is shear stress and the other is viscosity. So for a gas, somehow, if there is a force applied on the system, so let's consider a force, say, applied on a layer of the gas, and that the gas somehow is going to resist the deformation due to this shear stress. And actually viscosity is a sort of a measure of the resistance of the material to the deformation. Okay. And let's make another sketch to illustrate more. Let's say we consider two layers within a gas. There's on one layer, it's a reference layer with force equal to 0, and then there is another layer within the gas where some shear force is being applied, so F is not equal to 0, and there is a shear stress, and this shear force kind of lead to some sort of steady velocity. It's a force which is applied on a layer, and because of this force, that layer, let's say any gas on that layer, is going to have some additional velocity, and that additional velocity, let's say it's u, it is a kind of a steady velocity due to F. U is some steady speed or velocity due to the shear force F. Okay, so if any molecule happens to find itself on this layer, then it's going to have somehow some additional velocity on top of the kind of Maxwell-Boltzmann sort of speed. There's going to be some additional velocity due to the shear force F. Okay, if we consider the vertical axis to be, let's say, z direction and the horizontal axis to be x direction, the effect of this shear force is maximal at this layer where the force is being applied. But as we move on, as we move up the z-axis, this effect is going to be less and less and minimal at the layer where we have a reference layer where, let's say, f is equal to 0. Okay, and because of this shear force, one can imagine that this additional kind of speed on molecules, its average, if we call it like that, u of x, and we're considering the velocity, the speed in the x direction, it's actually going to be a function of the direction, the vertical direction z, right? So it is maximal somehow. If I can sketch something here, let's say it's maximal at the layer where the F shear force is being applied. The value is going to be u, okay? But then as we move on up the ladder in the z direction, it becomes smaller and smaller. Somehow there is going to be some sort of gradient, right, as we go up in the z direction, right? And the dependency of this additional velocity on z is what I have sketched in a red color here. So the more we go up the z direction, the values of u becomes smaller and smaller, right? The main point here to be mentioned is that there was a proposal that the shear stress, if we call it tau z x, okay, so the x demonstrates the direction of the shear force, and z somehow is the direction of change in momentum, right? So one can consider that as molecules sort of moving from this layer where f is equal to 0 upwards towards this other layer where f is equal to 0. So the initial layer where f is not equal to 0 upwards towards the layer where f is 0. The velocity, additional velocity due to the shear force changes, right? So it's a sort of a change in momentum, okay? So z, x is direction of force, direction of shear force F, and z is in kind of direction, flux direction. Okay, there is a change in momentum. So actually it is transverse. Okay, some sort of change in transverse momentum. But anyway, this the proposal is that the shear stress is actually directly proportional to the change in this velocity ux with respect to z direction. Okay. This proposal is by Isaac Newton. We can write okay, so tau zx by definition is going to be the shear force divided by the cross-sectional area of the layer, and we can expand this to be minus eta partial ux partial z. So tau, the shear stress, is directly proportional to the rate of change of ux with z, and the proportionality constant is eta, and we have a negative sign here because ux decreases as z increases. As we go up the z direction, the magnitude of ux becomes smaller and smaller, and that's the reason for the negative sign. So here where eta is the constant of proportionality, and it is called the coefficient of viscosity, or just simply it is called the viscosity of the system under consideration. Yeah. And just a note here to mention that ux, we actually considering an average, since the velocity imposed on the gas molecules due to the shear force F will be somehow something added on top of the Maxwell-Boltzmann motion of the gas in the x direction. So instead of using just x, we use the average value of x, right? Of average value of ux. Okay, so this is definition of viscosity, or the coefficient eta, and the target is that we should be able to kind of derive an expression for eta using kinetic theory of gas. So this is going to be a prediction from theory, and the coefficient of viscosity is something which can be measured experimentally. Okay. Now, to dive into the theory, one can consider this definition. Now, using this definition that the shear stress tau is equal to the sort of change in transverse momentum along the z direction divided by area times time. This is something we have seen earlier, and one can say define this to be, let's say, phi of z. So using the definition above, we can for sure write that phi of z is going to be minus eta partial average of x partial z. Now the task is going to be that we should be able to derive an expression for pi of z using kinetic theory of gas. So let us derive an expression for pi of z using Kinetic Theory of Gases. From there, if we have an expression for pi of z, then we can compare it with the right hand side of this equation, and then from there we should be able to have an expression for eta, the viscosity. Okay, in order to do that, we're going to consider a gas molecule which is traveling at an angle theta with respect to the z-axis. Okay, let's say this is z-axis, and then there is a molecule traveling with v at an angle theta, right? Okay, if we consider that the molecule, let's say, moved from this point, which I'm sketching, and let's say from a point where we have a reference layer to another point on another reference layer with a higher value in the z direction, right? And since there is a change in velocity as we go up the z direction, then there's going to be some sort of change in transverse momentum, or we can consider that the particle or the molecule is actually transferring some momentum due to shear stress. Okay, and if we assume that let's say the particle moved just before colliding, the molecule moved just before colliding with another molecule, so we're going to consider the distance covered somehow to be lambda, which is the mean free path, right? So if the distance, the molecule moving at angle theta with respect to the z angle, with the z axis, just before colliding with another molecule, then this interval along the z direction is going to be equal to lambda times cosine theta. Okay. With this sketch, one can write that the transverse momentum transferred by the molecule due to some shear stress under consideration, which is tau zx, since the molecule's last collision, okay, the amount of momentum transferred is going to be equal to minus m, negative sign, because the average of ux decreases with z, so partial ux, average ux, partial z times lambda cos theta, right? So if we know the rate of change of the velocity due to shear stress times the distance covered, so this rate of change is with respect to distance along the z direction times the distance covered by the molecule along the z direction. This is going to give us kind of the change in velocity somehow. And then mass times change in velocity is going to be the change in momentum, or the momentum transferred by the gas molecule. Now, if you recall that the gas molecule flux, as derived earlier, is given by this expression of V cos theta and f of V dV times 1/2 sine theta d theta. Okay, so this number of molecules per unit area, per unit time, and each of these molecules is going to transfer a quantity of quantity of transverse momentum, which is given by the expression above, right? So each molecule is going to transfer transverse momentum. This is the quantity transferred. And if we consider a flux of molecules, not just one molecule, then we can compute the total, we can compute pi of z, the total change in transverse momentum by the different molecules, all summed together. It's going to be the integration from 0 to infinity, integration 0 to pi of v cos theta and f of v dv 1/2 sine theta d theta times minus m partial ux partial z lambda cos theta, right? So if we sum over this individual transverse momentum transfer by molecules, then we're going to have what we need. Okay, and see here that theta is within is going to be within 0 to pi, since we want the sum of molecules traveling in all possible directions. Okay, so doing this integration, it can be done. This is going to be 1/2 nm times lambda times the average speed times partial ux by partial z. So if we compare with pi z equal to minus eta partial ux by partial z, then we're going to see that the viscosity eta is 1/3. Sorry, there's something missing here before the comparison. There is the part, the integration of the part with the angles have been missed. So here there should be so integration over dv of n of f of v times v is what is going to give us the average speed. Then this integration from 0 to pi of so this is going to be cos squared theta sine theta d theta, right? This integration, like you can check, is going to be equal to 2/3, so that the final integration is going to be minus 1/3 nm lambda average speed partial ux by partial z. So we're going to compare that with the definition we've had earlier. Sorry, that pi of z is minus eta partial ux by partial z. Then comparing this with the expression we have here on the right hand side for pi of z is going to imply that eta is excuse me, 1/3 nm lambda times average speed. So this is very nice. You see, using kinetic theory of gas, one can have an expression for the viscosity, okay? Or actually one can write the viscosity eta as 2 divided by 3 pi d squared m kbt divided by pi whole square root, using the definition of the mean free path lambda to be 1/square root of 2n times sigma, and average speed to be 8 kbt divided by pi m all square root. And also if we use sigma to be pi d squared, where d here is sort of averagely the diameter of the molecules, right? So this is an expression for viscosity, and one can see that viscosity eta is independent. As from this equation above, we can see that it is independent of pressure, right? And that eta is directly proportional to the square root of temperature, and we have for this derivation something which is very important, is that we have assumed, it has to be under this assumption, that L, kind of the size of the container of the gas, is really much bigger than the mean free path of the gas, and the mean free path of the gas is much bigger than the diameter of the molecules d. Okay, I think that's it. Just one more thing to mention, that gas for a system with L, which is smaller than the mean free path of the gas molecules, then the molecules would really kind of collide with each other. Instead of colliding with each other, more often they're going to collide with the wall of the container. Okay, and such a system has a name. It's called Nosten gas. So if the container is really tiny, if you're looking at molecules within a system contained in a very tiny let's say container, so the length scale of the container is far less than the mean free path of the gas molecules, right? So what's going to happen is that the gas molecules rarely collide with each other. Before they find one another to collide, they see the wall of the container more often. Okay, I think that's it for today about viscosity, theoretical derivation for the expression of viscosity based on kinetic theory of gas. See you next time, and goodbye for now.